Welcome to the 8th episode of our jet engine series. We are at the last component remaining, the nozzle. This is where the energy from the exhaust gas will be transformed into kinetic energy to generate thrust. Let's dive right in!
3, 2, 1, top.
3, 2, 1, half, the Flight Test Engineering channel.
In our second episode, the inlet, when we were talking about mass flow, we briefly touched on the point of compressible choked flow. We're now at the last main engine component of this series, the nozzle, and mass flow is one of the most important aspects here. After all, it is mass flow and speed of the gases going out the back that will produce thrust. Now, if we want to understand the flow mechanisms that dictate the engine operating conditions, we need to dig deeper and have a good grasp of compressible flow in nozzles. Let's start with a simple setup here. Suppose that on one end we have a tube open to the ambient, and on the other end we have a big vacuum reservoir that can be kept at very low pressure by very powerful pumps. Air can enter the tube and flow into the low pressure vacuum, and in between we have a transparent convergent divergent nozzle where we can peek into what's going on with the flow. We can control the amount of air passing in the nozzle by opening and closing a valve at the end of the tube right before the vacuum chamber, which is right there. As we open the valve and the flow starts, for now, let's just assume that there are no losses here. And in the tube, no boundary layer effects, no heat transfer, etc. So the flow starts slowly with pressures close to atmospheric pressure all along the tube here. And remember, the low pressure end is the vacuum chamber. Everything else is in the atmosphere here. As we open the outflow valve more and more, the flow will increase its velocity. And it's fairly intuitive to see this, that as you open here, our air particles are going to flow into the tube with more and more speed. So as we open the valve and the particles start to accelerate, is there any limits to what will happen? If we fully open the valve, are the particles going to accelerate indefinitely, or from your intuition, they're going to stop at some point accelerating and will reach some sort of equilibrium? Well, it turns out there is. And what happens is that the pressure drop traveling upstream from the vacuum side can only go as fast as the speed of sound. Remember that sound is nothing more than pressure waves. I've started my particle simulation here, and this is only for illustration because it's not really physics accurate. So if I let go of my simulation here and we start opening the valve, let's put 20% for example, we can see that very few particles flow into the vacuum sphere. And as we open it more and more, 45, of course, we would expect more and more particles to flow into the sphere. And if we fully open, yes, more and more particles are going to flow and accelerating the flow on the throat here. But as we said, this is going to have a limit. This is going to have the limit when the flow reaches Mach 1 here, right at the throat. That's going to be when the flow is going to be said to be blocked. So let's recall the mass flow equation and figure this out. We start by the definition of mass flow here, which is m dot equals rho a u, which is the area and the speed of the fluid. But the speed of the fluid, u, can be written in terms of Mach number, m times a. And a is the speed of sound, which in our case for our ideal gases is going to be square root of gamma RT. Then our m dot can be written as rho am times square root of gamma RT, which is a. We can then substitute density from the ideal gas law, where density is P over RT. So we have our mass flow equals P over RT times area, times Mach number, times square root of gamma RT. We can simplify a bit by placing the RT under the square root, like so. But we have here static pressure and static temperature, which will be different for each fluid velocity. So let's make this dependency explicit by using the values T0 equals T times 1 plus gamma minus 1 over 2 Mach squared, and P0 equals P times 1 plus gamma minus 1 over 2 Mach squared to gamma over gamma minus 1. We can now substitute back and get this nice expression for mass flow, which I'm not going to read. We can simplify it a little bit and get this as well. Notice that the dependencies here are physical parameters that are throat area, gas is the gamma and the R, and the state of the gas, P0, T0, and Mach number. So how does mass flow change with these values? Well, it will increase with P0 increase, it will decrease with T0 increase, and it will increase with more area on the throat, of course, because A is there. And what about Mach number? Well, Mach is a complicated function here, so it's not easy to see what happens with Mach. So it's easier if we plot this. Now, if we pick one gas and state, say air at sea level, and if we fix the throat area, we end up with mass flow varying with Mach number. So let's make a graph. We start by importing the usual stuff here, matplotlib, numpy, and set the dark theme and graph sizes. Then we can now create the function that will have the mass flow equation that we just saw, and throw in some numbers to run it. So let's say 20 millimeters diameter throat, which we need to convert to meters. And then we calculate the area and set P0 and T0 to sea level values, and also R and gamma for air. So let's run this. And we can then create a vector with a bunch of Mach numbers and call our function on it. So our Mach number is going to vary from 0 to 7, and it's going to have 100 values. And then we can straight call our function with the fixed values except for the Mach number. And finally, we can plot the data. So let's see what we get here. So nice, what do we have here? Let's see. This is really nice. For starters, we can clearly see that the maximum mass flow occurs at Mach 1, which is what we had before. Starting from 0 speed, it will increase, but after Mach 1, it will decrease again. Let's remember what we are trying to accomplish here. We're trying to understand what happens at the engine nozzle, where we have gas coming out of the turbine at a high temperature and relatively high pressure. Another way to look at this is by looking at the pressure ratio. So let's have a look. Another way to see this is by checking how low can the pressure downstream go before the flow reaches Mach 1. Recall that the stagnation pressure is given by this expression here, and we could look at the pressure ratio then, P0 over P, like so. But since the pressure at the throat is going to be lower than P0, it's easier to plot the reciprocal, meaning P over P0. So let's plot this pressure ratio versus Mach number here. Okay, nice. What do we have here? So we can see that as pressure ratio goes down, right there, the flow accelerates. But we say that the velocity does not increase beyond Mach 1 at the throat. In this case, if we substitute Mach 1 in the equation, we get what is called the critical pressure. And for air, this critical pressure here is going to be, or the ratio is going to be 0.53. Notice that we did not plot beyond Mach 1. So to summarize, when the flow is choked at the throat, if we lower the exit pressure even more, the fluid is unable to pass on this information upstream. This is why the mass flow does not increase. So no matter the lower back pressure, the nozzle will operate in the choke state and the mass flow will not increase. This is also why we saw in the last episode the turbine has a flat pressure ratio versus mass flow curve. And what happens after the throat is that the flow will need to transition from a choked state to a new state with even lower pressure. And it does this with an expansion shock wave, and this shock format will change according to the pressure. or the ratio. The lower the pressure, the more oblique the shock will be, and the famous Mach diamonds we see back the rockets will form. But this is subject for another time. Understanding this choking mechanism is key to jet engines because they generally operate in this condition, and if not at the nozzle, possibly at some passage in the compressor. To visualize all this, instead of showing you a simulation like I did, which is not physically accurate, I will show you instead the real deal. A movie clip made in 1965 by the folks of the National Committee for Fluid Dynamics Films. The clip was scripted by Caltech's professor Donald Coles and filmed at MIT's tunnel. This is an incredible piece of engineering art and you should watch it in full. The link is going to be in the description.
Room air at atmospheric pressure enters the channel here, flows from left to right through the channel, through this control valve, and into a vacuum pump downstream. Each column on this manometer board shows the static pressure at the corresponding point on the lower wall, the flat wall of the channel. We've arranged for the mercury level to go down when the pressure in the channel goes below atmospheric. Zero pressure is here. The first column always shows the stagnation pressure upstream, the pressure in the room. The last column always shows the downstream stagnation pressure, just ahead of the valve. At low rates of flow, the pressure is nearly symmetrical around the point of minimum area, called the throat. We can draw a continuous pressure distribution and interpret the curve qualitatively as velocity. This is because viscous forces are not important outside the boundary layers, and the fluid acceleration is determined by pressure forces alone. A falling pressure always means a rising velocity, and vice versa. The highest velocity in this flow is at the throat. If we increase this throat velocity, we come to a critical flow rate. The noise level suddenly changes, and the pressure distribution develops a corner at the throat. As we continue to open the valve, the symmetry disappears. Notice that the pressure and velocity upstream of the throat are not changing. Just downstream of the throat, the falling pressure means that the air is accelerating in the diverging part of the channel.
As I said before, this concept of mass flow being limited is extremely important because even if the compressor is trying to push more mass flow through the turbine, with the nozzle choked, this increase will be limited. Keep this in mind until the next episode, where we will go back and revisit the inlet mass flow assumption and create an iterative version of the code to obtain conversions, considering what is going on in the nozzle throat. Now, let's have a look at the nozzle equations we're going to use to solve this. On the channel's GitHub page, you can access the gas turbine propulsion repo, and then the Turbojet subfolder has the notebook episode 8 nozzle, with all the code and all the formulation in there. And if you prefer to download to your machine, just click this button up here. Links in the description. At the nozzle, just like the inlet, we assume adiabatic flow. So the total temperatures T05 and T08 are the same. Next, we know the nozzle will dissipate energy from the flow through friction, the same way as we modeled on various components already. So the nozzle efficiency is going to be defined by the actual temperature drop, T05 minus T8, over the ideal temperature drop, T05 minus T8 prime, as if the expansion was isentropic. We can rearrange this to isolate the actual temperature drop, T05 minus T8, and let's keep this aside for a moment. If we recall the isentropic pressure-temperature change relationship, we can include the pressure ratio in our equation. And why is this important? Well, because that is easy to get from our nozzle conditions. At the end of the day, the exhaust gas going through the turbine will result in a pressure drop, and since the next step is to expand the ambient to ambient pressure, we have the pressure ratio defined. With this, we will be able to have a means to calculate the exit temperature given the pressure ratio. And because we're talking about isentropic conditions, we write T8 prime over T05 equals P8 over P05 to gamma minus 1 over gamma. And we can isolate T8 prime and get T8 prime equals T05 times our pressure ratio to gamma minus 1 over gamma. So we can now plug that back into the efficiency equation and we get T05 minus T8 equals nozzle, add eta nozzle, times T05 times 1 minus 1 over the pressure ratio to gamma minus 1 over gamma. Now, we will need to account for two cases here, choked and non-choked flow. So let's figure out the choked case first. In this condition, we know that the Mach number at the throat will be 1. And we define the pressure that this occurs at as being the critical pressure, PC, together with the temperature, TC. If we recall the energy equation and write the relationship between total and static temperatures, we get T08 over T8 is 1 plus V squared over 2 Cp T8, which can be written in terms of Mach as 1 plus gamma minus 1 over 2, Mach squared, right there. And because we assumed no heat exchanged through the walls, T05 is equal to T08. And so the ratios are also equal. T05 over T8 equals T08 over T8. Just recall that for choked flow, we have P8 equals PC, T8 equals TC, and Mach at station 8 equals 1. So if we set Mach to 1 on the relationship for T05 over T8, we get T05 over T8, which is the same as T05 over Tc, equals 1 plus gamma minus 1 over 2, which is gamma plus 1 over 2. And this is very interesting here because that only depends on gamma, nothing else. We can then recall the nozzle efficiency equation, eta nozzle, and instead of using T8, we use Tc, and we get Tc prime is T05 minus 1 over eta nozzle times T05 minus Tc. We can then plug this back into the isentropic pressure relationship, and we can get Pc equals P05 times Tc prime over T05 to gamma over gamma minus 1. But we can exchange Tc prime for Tc, right there, from the efficiency equation above, and we can then obtain P05 times 1 minus 1 over eta nozzle times 1 minus Tc over T05 to gamma over gamma minus 1. We can go even further and eliminate the Tc over T05 because we have this relationship, and we get P8, which is equal to Pc, as P05 times 1 minus 1 over eta nozzle times gamma minus 1 over gamma plus 1 to gamma over gamma minus 1. Phew! We have now a way to calculate the critical pressure and critical temperature from the pressure, temperature, and fluid properties P05, T05, and gamma from the gas coming out of the turbine. Just for completeness, here's a few basic equations that we will use as well. V, Mach, rho, and m dot. So now we need to look at the other case where pressure coming out of the turbine is lower than the critical pressure. In this case, we do not need to calculate P8, and it will be equal to the ambient pressure. All we need is to get T8 from the same equation we had before. T05 minus T8 equals eta nozzle times T05, 1 minus 1 over pressure ratio to gamma over gamma minus 1. And we can isolate T8, and we get T8 equals T05 minus eta nozzle times T05 times 1 minus 1 over the pressure ratio to gamma minus 1 over gamma. It is more convenient to calculate speed from delta T instead of Mach. So here we have the equation as well for this case, V equals square root of 2Cp delta T. So the last piece of the puzzle is the thrust equation, right there. After all, this is the one thing that we want to know, right? The specific thrust produced by the engine will be the delta velocity of the fluid plus an additional term that depends on the pressure. So F is going to be equal to V minus Vi plus A star over m dot times P8 minus P ambient. So as a convention, A star is used for the area of a blocked nozzle. It is the same thing as A8 for us. Note that this last term is only more than 0 when we have choked flow and the exit pressure is higher than the ambient. And now it's time to implement this in code. Let's go to the engine parameters definition cell on the top and add a few numbers here. We need to add the nozzle area, A8. We're going to choose 0.25 square meters in this case. And the nozzle efficiency, eta nozzle, which we're going to choose 0.8 for this case. And now we can go down to the nozzle. So cell number 14 here. Right there. Our function will get the gas object, the Mach, eta nozzle, which is the efficiency, ambient pressure, throat area, the aircraft speed, and the Cantera gas object that will communicate back the states when we go back. Scrolling down past the function documentation, we have the entry conditions here. We start by calculating the properties for the gas coming in. So we get gamma, the gas constant R, the stagnation pressure and temperatures coming in. Then we get the critical conditions, and since we will need to decide if we have sonic flow or not in the throat, we need to calculate the critical pressure, PC. Now we can check if the actual pressure ratio is lower or equal to the critical pressure ratio and branch for the choked or non-choked cases. If it is choked, we set the choked flag. Then we calculate the pressure out, PC, which is equal to P8 in this case. We calculate the critical temperature, Tc here, or T in this case. Then we calculate the flow speed, which will be the speed of sound squared root of gamma RT. And remember that Mach is going to be 1 in this case because we're blocked. Then we calculate the density, then the mass flow from rho V A star, and the specific thrust delta V plus A star over m dot times delta P. If it is choked, then we set the flag to false. The exit pressure is going to be our ambient pressure. We calculate T8, then the flow speed, density, mass flow, and finally our specific thrust here. Notice that in this case, because we don't have delta P, we only use the first portion of the specific thrust, which is the delta V. And before returning the results, we update the gas properties, and if the flow is not choked, calculate the Mach number going out. And we returned our choked flag, the calculated mass flow, Mach number going out, and the specific thrust. And okay, it's ready to run this. Let me scroll down to number 15 here. Right there. So we're going to call our nozzle function with the gas coming in from station 5, the turbine, and the parameters we discussed, Mach, eta nozzle, ambient pressure, A star, aircraft speed, and the gas out object. Note that the index here, number 6, is stored as station 8 in our list. We can see a few lines of code that are commented out here. Let's ignore them for now, and they will make sense in the next video where we will iterate and converge on the mass flow. For now, let's just print out the delta in mass flow, which is the difference between what we have calculated right now, as the limited by the nozzle throat, and what we had gassed initially. Then, as usual, we append the properties to our collector list, TP and composition X. And let's print out some more information here. The thrust, note that to go from specific thrust to thrust, we multiply by the mass flow here. So this will be F times m dot, and let's divide by 1000 to get back kilonewtons instead of newtons. Let's print the altitude and ambient temperature as well. And on the next line, let's print the calculated mass flow in kilograms per second. And the fuel flow can be calculated from mixture fraction as mixture fraction over eta B times m dot. Recall that eta B is the burner efficiency from our combustor episode. And now we can obtain thrust-specific fuel consumption, which will be the fuel flow divided by the mass flow divided by specific thrust. Let's print out the fuel flow in kilograms per hour now, and TSFC in kilograms per kilonewton hour. And last, we can obtain the specific air range by dividing the aircraft speed by fuel flow. But we get this in meters per kilogram, which is not useful. So let's convert that to more aero units, nautical miles per kilogram. That's what we're going to have here, nautical miles per kilogram. Right. So let me run all the cells above this one. Okay, so we can see right off the bat that our 20 kilograms per second mass flow that we guessed was off by 3.9 kilograms per second, and that's roughly 20% off. This is exactly why we need to close the loop on mass flow in our next episode. So stay tuned for that. Our results here show also that we have 11 kilonewtons of thrust at 35,000 feet in Mach 0.8. We get the fuel flow around 1,000 kilograms per hour, and our TSFC at 90 kilograms per kilonewton hour. And the SAR, the specific air range, is going to be around 0.46 nautical miles per kilogram. Don't worry about these numbers now, because they will need to be converged with mass flow. So we'll refine them on the next episode, like we said. Finally, let's print out all the results here from the stations and make our graph. We can see that the temperature drops, so does the pressure, as expected. But the gas velocity is what is interesting here. It is operating at choked state Mach 1, right there. One could ask, but wouldn't it be worth it to have a convergent divergence nozzle at the exit to better use this excess pressure and further accelerate the gas? Yes and no. From the ideal point of view, yes, the faster the gas, the more thrust we get. However, when we factor in the friction we would lose on the divergent portion of the nozzle, unless there's a lot of energy to further expand the gas, it turns out it's not worth it. This is why we do not see convergent divergent nozzles in jet aircraft, only in rockets. Here we have also the nice graph we had, starting from the nozzle, compressor, and now we have finally the expansion on the nozzle here, bringing the pressure very close to ambient. And this is what we wanted. And this brings us to the end of this episode. As usual, if you want a copy of this notebook, visit the channel's GitHub page. Link is going to be down below. On the next video, we'll close the loop on mass flow and refine our results. See you there!